Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a theoretical physicist currently doing a postdoc in the Helsinki Institute of Physics over in the University of Helsinki in Finland. And yeah, I'm a cosmologist, so that means that I study the universe, the contents of the universe, how everything evolves, how everything interacts, all of the fun stuff happening inside the universe. It's great to be a cosmologist. We get to study really, really cool things. And it has been a very, very, very big week in cosmology. Sometimes I start these streams like, well, nothing new. Science is slow and gradual, which it always is. It's a slow and gradual progress. But there are some weeks that stand out. There are some moments that stand out. And this week we had three massive things in cosmology. I already talked about them a bit last week, kind of what you might expect. But now we have three massive things that have happened this week. And today, obviously, I have to talk about these things. So as always, hello to all of the regulars. Welcome to any first-time viewers. Great to have you all here. As usual, please do the usual YouTube things, like the video, subscribe, leave a comment. It all helps to boost engagement and the usual blah, blah, blah things, especially as I'm probably going to lose all the Twitter viewers today because Twitter is a dumpster fire. So please do, you do all the usual things to help get people onto the stream. It's always much appreciated. So for anyone who doesn't know how this works, this is an interactive stream. The idea here is that you can ask me anything you want, and I will do my best to answer. Of course, I do not have all of the answers. I will not be able to answer everything, but I'm going to try to answer any questions you have. And as always, jump in at any point with questions, with comments, with things you want me to do to derail me and take me off on random tangents. Those are also always, always, always welcome. So we have three big things. And of course, I need to start with no, we didn't find dark matter. No, it's not aliens, because no, we have not found dark matter yet, and it's never aliens. But someday it might be dark matter. It's not dark matter. Also, if it were dark matter, I would have started with we found dark matter. We have not yet found dark matter, but we launched a satellite that is going to help us with that. So, three big things this week, and we're going to talk about all of them. The one I'm the most hyped about was yesterday, the Euclid spacecraft launched. It was an amazing launch. We're going to talk about that in a lot of detail. IceCube released some amazing results. First image of the Milky Way seen with neutrinos. Very, very cool. And of course, there was the nanograv and other pulsar timing array experiment announcement, where they have found for the first time ever, they have measured the gravitational wave background out there in the universe coming from supermassive black holes smashing together. Each of these things individually could be a whole stream. So today we're going to do like 15, 20 minutes for each of these. Probably going to spend a bit longer on Euclid and on nanograv because both of those are amazing things. No alien megastructures today, at least not to my knowledge. No dark matter. We found dark matter, not yet at least. But we have three really, really cool things to talk about. So the first one has to be yesterday's launch. I know it was inconveniently timed that Twitter went down just when the launch was happening. So if you were hoping to get live tweets of it, sorry, Twitter was down. But it was an amazing launch. So let's take it slow. Let's walk through what is Euclid, why I'm hyped about this, why it was an impressive launch, and how everything went yesterday. So let's jump straight into Euclid. So let me just bring up my images as always. And no, this is not the one we want. We want Euclid, the Euclid Space Telescope. So Euclid, this ARCIS rendition that you can see on the screen here, is a telescope by the European Space Agency, mainly with some other funding sources, but mainly European Space Agency. And it has two missions. Euclid has two main missions. One of them is to map galaxies out to redshift about 10. So this means that it's going to be looking at things that are 10 billion years away. Sorry, not redshift 10, redshift 2 point something. Galaxies that are 10 billion light years away. It is going to basically look back in time 10 billion years, which is amazing. So Euclid is going to map galaxies out to a really far, far distance. And it is going to get the velocity and the movement of a lot of these galaxies as well. So it's hoping to answer two main questions. How does the mass in the universe behave? So basically, how does dark matter behave? And how has this changed over the history of the universe? Which basically means, how does dark energy behave? So if we go to our usual chart that I have somewhere and move to the wrong, where's my other figure? Use your pie chart. We know that the universe has three main components. Everything you see, everything you're accustomed to, everything from me to my very hot tea, we're all normal matter. Normal matter only accounts for about 5% of the energy budget of the observable universe. Then there's 26%, which is in the form of dark matter. Dark matter is this weird type of matter that is interacting gravitationally but doesn't interact electromagnetically. That means that dark matter does not emit light, it does not absorb light. As far as light is concerned, dark matter is not there, except when it gets deflected because of gravitational effects. So dark matter is basically invisible, but it's the invisible matter that holds galaxies together. Without dark matter, we can't explain why galaxies look the way they do or why the universe looks the way it does. At least we haven't found a better reason yet. The remaining 70% is in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe. It's pushing everything outwards. And that's pretty much everything we know about dark energy. It's very difficult to study dark matter and dark energy, except enter Euclid. Euclid, this guy here, this telescope here, is going to try to map galaxies up to 10 billion light years away, 10 billion years into the past, and it's going to try to find where these galaxies are, where they were before, and everything that's happened in the meantime. So this detailed map of galaxies that far out in the cosmos is amazing because it will really allow us to see how dark matter is behaving and how dark matter has behaved in the past and how dark energy is bringing everything together. So a lot of people think, or a lot of people say that Euclid is basically the make or break for a standard model of cosmology. What I just showed you before, this pie chart, this is the standard model of cosmology. Not much normal matter, a lot of dark matter, and a lot of dark energy. So what happens if Euclid goes up and doesn't find these things? What happens if it finds something that is not compatible with dark matter or with dark energy? It is basically going to be a really big check test of the geometry of the universe. It's going to be amazing. And Euclid is a mission that when I started my PhD, Euclid was like this far off thing, right? You like how in that pie chart is 100% visible instead of 5%. Yes, well, if I made the pie chart with like only 5% visible, it would be quite hard to see, but it would be more realistic. So when I started my PhD, which seems like a very long time ago by now, it was indeed 7 years ago that I started my PhD. Wow. Euclid was like this far off distant thing that was going to happen someday. It's like, yeah, someday we'll get Euclid. It's going to help us solve the mysteries of dark matter and dark energy. It's going to help us understand the cosmos someday. And that someday is now. Euclid launched yesterday. And it was an incredible launch. Everything went according to plan. So yesterday was the first launch window. They said it was supposed to launch last year from a Russian rocket, and then, of course, stuff happened, and they changed their plans. So instead, it was decided that it would launch from a Falcon 9 from Cape Canaveral at some point in the summer. And then middle of June, or close to the end of June, the Euclid team put out an announcement saying, launch window opens 1st of July at 11 minutes past 5 in the afternoon, Central European time. That's what we're aiming for. So that was their first chance. And, if you've watched rocket launches by now, there's always delays, there's weather, there's an exhaust pipe they want to check, there's always something. Wasn't the case with Euclid. Euclid launched at the first minute of the first launch window. It was a spectacular launch. If you didn't watch it live, it's worth watching the replays because as launches go, this was a pretty spectacular launch. And yes, indeed, it's going to be testing Euclidean geometry, hence why it's called Euclid, named after the Greek mathematician. It was an absolutely incredible launch. Yesterday at 10 past 5 Central European time, 12 minutes past 5, we got this. Euclid went up on a Falcon 9 rocket, and it was spectacular. Everything went according to plan. And I was so stressed. I was at a watch party in my office together with people who were literally working on Euclid mission. I'm interested in it. I love Euclid, but I'm not actively involved in the Euclid data. But there were people in my office who are, like the Euclid team in my office was there. A bunch of us gathered to watch the launch. It was really fun. We had a launch party. Everyone brought snacks, and you could feel the tension in the room. Yeah, when the launch happened, we were all, at this point, we were all holding our breaths, just waiting. It was an amazing launch. They kept saying like everything is nominal, and everyone in the room was like, nominal. We like the word nominal, but this is good. And a few minutes after launch, the first rocket launches are always nerve-wracking, and when there's a €2 billion spacecraft on the top of the rocket launch, that is the next big thing in cosmology. It was very nerve-wracking. Some people in the office were like, I have not slept in a week. You could see the live stream of the people actually at like mission control in Germany. The nerves, you could feel everybody's nerves. But it was a perfect, flawless launch. A few minutes after launching, there was a separation. The first stage separated, came back to Earth. And as Falcon 9 landings go, it was a perfect landing. SpaceX, I don't like SpaceX, but they nailed the landing of the first part. It came down amazingly on the platform. Really nice to see. And then we had the nerve-wracking wait because we were not going to celebrate. Nobody was going to celebrate until it had detached from the second stage, was off by itself, and had called home. So we were waiting for Euclid to call home before anything could be celebrated. So if you look here, this was 16 seconds after launch, went up. At this point, we were still like, okay, hold our breath for a while. Then 40 minutes after launch, we got the deployment. So the second stage broke away, and there were cameras attached. We had spectacular views of the Earth and of the satellite. And this here is basically the last image we're ever going to get of Euclid. This is Euclid heading away from the second stage rocket. The second stage rocket then, has done its job. At this point, Euclid, this thing you can see heading away, is on its own. It has its own thrusters, but that's it. It's gone. It's on its own. So at this point, 41 minutes after launch, we were like, okay, Euclid is by itself. At this point, if anything goes wrong, there's literally nothing we can do about it. So at this point, we were still like, okay, things are going well, very well, suspiciously well. And then you could just feel everyone was holding their breath, waiting. If you were watching the live stream, this is the point where it turned to a signal that was flat, and we were waiting for a bump there that was going to be Euclid. And about 45 minutes after the launch, we saw the jump on the signal and heard the reassuring phrase from mission control, we have telemetry from Euclid. Euclid phoned home. And at that point, we started celebrating. We popped out the champagne. We all celebrated. It was amazing. Everything that could have gone well, went well. The mission seems to be going well. So Euclid is on target. It's heading towards L2. So L2 is one of the Lagrange points. It's basically a point where you can put a satellite and it's going to be happy there. Audio issues, please do let me know if other people are having audio issues or if it's just on James's side. It's always hard to tell if it's on my side or your side. So please do let me know if anyone else is having audio issues. And I'll use this break just to drink because I'm not doing that enough today. All good now? Okay, perfect. That is good to know. Whatever it was, maybe just technical glitch. Glad that that's resolved now. Audio is okay. Okay, thank you for letting me know. So Euclid is on its way to L2. L2 is one of the Lagrange points. Lagrange points are just fancy names for places where the forces keeping the planets in orbits around the sun and the motion and the gravitational force kind of balance out. So they're places where it's convenient to put satellites because they just kind of stay there. It's quite easy to keep them in orbit there. So if here's the sun, here's the Earth, L2 is over here, which also means that then the satellite can shield itself, use the Earth as a shield to block out the sun, which is of course going to get in the way of a lot of measurements. So Euclid is heading off to Lagrange 2, to L2. It's the same place JWST is. Don't worry, they're not going to crash. Someone at the launch party made the comment of, wouldn't it be funny if these two things crashed together? And everyone in the room was like, no, please don't even say that. No. So Euclid is heading off to Lagrange 2. It will take 1 month to get there, which means end of July should be reaching L2. And then it's going to, park itself in L2, start switching stuff on. They're going to gradually start switching the instrument on over the next month as it's journeying there. But once it reaches L2, there's then going to be 2 months of taking data, just test data, checking that things are working, turning on the right instruments, making sure it cools down enough. 2 months before it starts taking actual science data. And so that takes us to the end of July, August, September. So then in October, hey Ian, great to see you in the comments. Really nice of you to join. So then in October, it's going to start taking actual data. And then it's going to take data for 6 years. So Euclid is on its way to L2. In 3 months, it's going to start taking actual data. We expect before the end of the year, there's going to be a couple of images released. These will be like fancy pictures. They're not going to contain much science, but they'll be the fancy pictures. And then the first actual data of dark matter, dark energy measurements from Euclid should be out early 2026. Which is not that far away. It's like 2.5 years, and we'll actually get data from Euclid. So this is amazing. I'm super excited about Euclid. It's a really, really, really big thing for cosmology. It's going to help us understand dark matter and dark energy. It will also help us do things like measure the mass of neutrinos, which is fun. So it's a big experiment. It's one that could change a lot of things in cosmology. It's something that is really important if you study late universe or like dark matter, dark energy, all of these things. Euclid is a big deal. And it was a faraway future mission for a very long time. And now it's up there. It's up in space. It launched. Everything went incredibly well. It was an amazing launch. Now it's off. It's going. It's doing its thing. 2 months next, important point is making sure it gets to L2 in a month. And then it's going to start with the final checks and start taking data. So, it's been intense. On the watch party yesterday, there was a lot of tension, and then you could feel us all coming down like, phew, okay, let's go get some sleep now. And we're not even involved in it. I can't imagine how stressed the launch team were. But it's done. Euclid is up there. It's out. It's amazing. I can't wait until we get our hands on Euclid data. So there's another big mission in cosmology, the LISA one, the laser interferometer space antenna, which is a gravitational wave detector, which is the one that I'm involved in. It's going to launch in late 2030s. And it's not really looking at the same things as Euclid, because Euclid is dark matter, dark energy. LISA is gravitational waves. But they just successfully launched a rocket. It's always encouraging when we succeed at another satellite, at another telescope. Like, we really know what we're doing. I was going to say it's not rocket science, but it is rocket science, and we figured it out. We figured out how to get our rockets up there and our telescopes up there. So yeah, it bodes well for future missions, because it's just another proof that we can actually launch these things. So so I'm not officially part of the ESA LISA team, but I am part of the LISA consortium. So I am doing forecasts for what LISA is going to help us measure in the future. And I get to say that I'm part of the LISA consortium, which is pretty cool. But yes, when that launches in the end of 2030s, I'm going to be such a nervous wreck. I will absolutely not be live streaming that. I will be hiding away. So the earliest that we learn super cosmological breaking news from these launches, from Euclid, I think if there's any groundbreaking results, the earliest we can expect them is 2026. But probably if it is groundbreaking, then we'll want all of the Euclid data to confirm this. So then we'll want the full 6 years of data. So let's say it starts taking data in 23, it finishes taking data in 29, a couple of years of processing. Early 2030s, we should be done with data processing of Euclid as well. So 10 years from now, we'll have finished with Euclid, which is really cool to think about. So that was the big event yesterday. That was just one of 3 big events this week. It's been a week. So Euclid is up in space. Everything went well. I was expecting that there would be some delay and they would have to postpone the launch until today, but they didn't. They launched first possible date. It's gone, done. Mission accomplished, or mission started. We have a mission. There's a lot of random slogans they've chosen for Euclid. Like one that they were repeating on the stream, on the live stream, was like "into the darkness, into the dark universe." And then on Twitter, they had Dark Universe Detective hashtag going, which is super cringy, but I love it anyway. So yes, Euclid is the Dark Universe Detective. Into the darkness. It's going to be great fun. Cannot wait to see what it's going to give us. Okay, going backwards, what else happened? On Thursday, we had two big announcements, one from pulsar timing array people and one from neutrinos. And I'm going to do neutrinos first and then talk about pulsar timing array, which is an incredible result and one I'm super excited about. But first, neutrinos. Neutrinos are also very, very, very cool. So what are neutrinos? Neutrinos are part of the standard model of particle physics. They are a tiny, tiny, tiny particle that travels at almost the speed of light. So they're the smallest particle that we know of that still has mass, and they travel almost at the speed of light. Neutrinos barely, barely, barely interact with anything. They have basically no interactions except weak interactions. So this means that neutrinos constantly zip through you, through everything. If you hold up your thumb, every second, 60 billion neutrinos pass through the tip of your thumb. Every second, 60 billion of them. But you never notice because neutrinos just don't interact with anything. Another cool thing about neutrinos is they can change flavor. There are three neutrino flavors that we know of: the electron neutrino, the muon neutrino, the tau neutrino. And neutrinos have the cool thing that they can be created as an electron neutrino, and by the time they reach us here on Earth, they might have changed through muon to tau, back to muon to electron, up to tau again. They can just change flavor. It's really cool. And the ways we figured this out is fun to think about because we know how many neutrinos should be produced in the sun. So you can set a detector to measure neutrinos coming from the sun. And the first neutrinos we figured out how to measure were electron neutrinos. So someone did this and then realized that we were actually receiving like 1/3 the amount of neutrinos we expected. And it's because the other 2/3 had changed flavor to one of the other species of neutrinos. So very cool. When you say smallest particle, does that just mean mass or is it their diameter? When I say smallest, I mean mass because particles don't actually have a size. So when we're talking about particles, we always treat them as points because it's quite hard to think about the size because quantum physics gets blurry and messy and everything is fuzzy. So when we're talking about size, I generally mean mass. So they are the lightest particle that we know of that still has mass. We know there are massless particles like photons, particles of light, but neutrinos are the lightest particle that still has mass that we know of. And neutrinos are produced by a lot of different things, like a lot of processes in the center of the galaxy produce neutrinos, a lot of processes in suns, in stars. High energy neutrinos can come from anywhere. Is all that extra newly discovered neutrino energy accounted for in our theories? Yes. So the neutrinos, initially we didn't expect neutrinos to have mass, and the standard model of particles of physics said that neutrinos were massless. Then we found that they change flavor. If they change flavor, they have to have mass. Now the mass is incorporated into the standard model of particle physics. But neutrinos, as I just said, are really difficult to do anything with because they just pass by undetected. But occasionally you might get a neutrino interacting with something else. And if this happens, for an example, in a massive detector, you might be able to measure them. If we can slow down light, can we slow down neutrinos? Not that we've been able to figure out much yet, no, because light usually slows down when it cannot travel freely through things. Neutrinos just keep passing through everything. They do not care. They're just going to zip through everything unnoticed. What property is different with neutrinos and antineutrinos? Great question. Hey, David Dunn, great to see you as well. So an antiparticle is a particle that has opposite quantum numbers. So if you have something that is spinning up, you can have something else. Sorry, something that has positive charge, you can have something that has negative charge. They come together, they can annihilate. For an example, an electron is negatively charged. Its antiparticle is the positron, positively charged. You put these together, they annihilate and they produce radiation. So an antineutrino would be the antiparticle of a neutrino. We're not yet sure if neutrinos have antiparticles, and if they're their own antiparticle, we're still working on that. But so protons and electrons are the same size as quarks, even though they're made up of them. We consider them to be point-like, but we also consider that you can measure things like the radius of an atom. So, we can calculate, or we can approximately calculate the overall area where the radius of a hydrogen atom should be. But yeah, we treat particles as points because it's easier. So we know that protons are much more massive than electrons. We know that protons are made up of quarks, but these are points because quantum physics is fuzzy. So we don't talk about the size of protons. Okay. Neutrinos pass through everything. except black holes, because black holes are just big, huge gravitational wells. They affect everything in space-time, and neutrinos are still subject to the laws of space-time. So they also get sucked into black holes. Neutrinos cannot pass through black holes, to our knowledge, because too much gravity. So one of the most amazing experiments we've built here on Earth, in my opinion, is IceCube. IceCube is 1 kilometer cube of detector built 1.5 kilometers under the ice in Antarctica. They basically drilled a bunch of holes, about 324 holes in the ice, drilled down 1.5 kilometers in each of these holes. Sorry, 2.5 kilometers. And then they inserted cables with detectors added onto these cables. These detectors are what we call why did I try to say the name? I don't remember the name. They are these DOM detectors. Please do not ask me what that stands for. These like little spheres that can detect light. You put them on the string, you feed it down the hole. So you have this big string with the detectors on it. You feed it down the hole, 2.5 kilometers under the ice. You put like 324 of these strings, and you have yourself a neutrino detector. How does this work? Well, the idea is if a neutrino is traveling through the ice and interacts with something in the ice, for an example, with a muon or something like that, it can trigger a chain reaction, and the end result is you get a flash of light. Based on how this flash of light moves through the ice, you can figure out where it came from. Based on the pattern, you can figure out if it's a neutrino. So we can use this detector, 1 kilometer cubed of detector built underneath the ice in Antarctica, and we use this to measure the lightest particles that we found. It's amazing when you think about it. And IceCube has already found a bunch of things. For an example, IceCube has been able to find a lot of neutrinos in our solar system, which it usually tries to filter out because those are the noise. IceCube has been able to find at least 7 high-energy neutrinos coming from beyond our galaxy. These are high-energy neutrinos that are so energetic that they've traveled to us from a distant galaxy, which is amazing. So IceCube has been able to find a lot of cool things. So when IceCube called a press conference last week, it was like, okay, they found something. So IceCube has indeed found something. And what they found is pretty impressive. If you consider every image you've ever seen of the Milky Way, it's always using photons, particles of light. It's always using the electromagnetic spectrum, right? Even if you're using, hey, Abyss, great to see you as always. Really nice of you to stop by. And hello to everyone else I didn't say hello to. I was caught up in Euclid and didn't say hello to everybody, but hello to everyone here. So every image you've ever seen of the Milky Way is using light. You might have seen gamma rays, X-ray versions of the Milky Way, infrared, ultraviolet, visible light. But all of these are just different energies in the electromagnetic spectrum. It's using photons. But we know that the galaxy is also emitting neutrinos. There's so many stars, there's so many processes. If we look along the line of the Milky Way in the night sky, we expect to see more neutrinos than if we look elsewhere. If you look towards the center of the galaxy, we expect to see more neutrinos than if you look elsewhere. So wouldn't it be amazing if we measured enough of these neutrinos to actually map the Milky Way using neutrinos? It would be pretty cool, right? But can we actually do that? Well, the answer is yes, we can. And here you have the first image. This is an artist rendition. This is not a real image, artist rendition. But this is looking towards the center of the Milky Way. And I do read your comments here, Smith. Don't worry, I am seeing you. I'm just not replying to many comments today because I'm rambling. This is the Milky Way seen with neutrinos. The blue light here are high-energy neutrinos coming from the center of the Milky Way. So we don't really see this blue light image. This is an artist rendition. But we have detected, or IceCube has detected, enough neutrinos coming from the center of the Milky Way that they can now map. Just using neutrinos, they can map different parts of the Milky Way. This is incredible. It's still, it's low significant data. We still need more neutrinos. We still need more data for this. But for the first time, we can look at our galaxy in something other than light. We can now use neutrinos to map out our galaxy, which is really, really, really cool when you think about it. So if you take the typical image that you might have seen of like the galaxy in X-rays, the galaxy in gamma rays, the galaxy in visible light, now you can add this line to it, the galaxy in neutrinos. So again, this is an artist rendition taking the data from IceCube and mapping it onto the galaxy. But This is a starting point. This is not the perfect high resolution image that we've seen with photons. This is step one, but now we know that it's a technique we can use. So over the next few years, they're going to be able to refine this. Hey, Paul, great to stop. Great of you to pop by. Always great to see you here. No, you didn't miss much. Just major spacecraft launch, first image of neutrino galaxy, and nanograph results. But don't worry, you can always catch the replay. How do we get pictures of the Milky Way from above if we can't send graphs out that far? It's based on math and assumptions. So indeed, when we can look into the center of the Milky Way, we can look into the arm of the Milky Way. If the Milky Way is on the plane like this, Earth is actually or the solar system is actually kind of tilted, which is great because then you get to see the Milky Way and away from the Milky Way, depending where you're looking. If you've ever had a spectacularly clear night sky, you might have seen the tail of the Milky Way. So that's how you can look at the Milky Way, and you can see how it looks looking in and looking away. And then using that, and based on everything we've been able to see of other galaxies, we reconstruct what our Milky Way should look like. But any photos you see looking into the Milky Way from above, this is a reconstruction. This is a series of assumptions and math and predictions. But the same way this one here is an artist rendition. So this is using the ice cube data of neutrinos and mapping it onto the Milky Way. It's a starting point. It's an amazing step. For the first time, we have an image of the Milky Way not using light, using something else, using a whole other particle. But there's still a lot of work to be done. This is the first step. It's a proof of principle that this is something we can do. Scientists will hibernate for 3 years waiting for the next results. Yeah, that would be fun, actually, if we could just like, oh, I'm going to sleep now. Wake me up when Euclid sends results. So you might look at this and say, okay, they don't have too many neutrinos, it's not overly significant, but it's amazing that we've been able to do this. This is like when people first turned on telescopes and could first see the Milky Way, and now we're finding a new way of seeing the Milky Way. It's amazing. And over the next 10, 15 years, this is going to get better and better. Or when we first saw Pluto, it was this tiny, tiny little blob. That's kind of where we are now. And now, if you look at the images we have of Pluto, we can see the little heart on Pluto's surface. So imagine how clear this Milky Way neutrino image is going to look 10, 15 years from now. New way of looking at the Milky Way. It's really, really, really cool. Yeah, we're not sure if the Milky Way has 3 or 4 arms. It's a problem of looking into or even 2, actually. It's a problem of the way we look. We're part of the Milky Way, so you can't remove yourself and look up from above. So it's quite hard to figure out how many arms the Milky Way actually has. It's fun. We don't think it's an octopus. It should have less than 8. But yeah, we don't know how many arms the Milky Way has. It's fun. But now we can stare at the Milky Way with something that is not just photons. So that's kind of cool. And I think this announcement would have been amazing if that was the only thing happening on Thursday, but it wasn't. So it kind of got a bit overshadowed by the other major announcement on Thursday. So before moving on to the other major announcement of the week, are there any questions about IceCube and neutrinos? Because it's really cool. It's really cool when the fact that we can now look at the Milky Way using something that is not light. Like we don't even need light anymore, and we still do need it, but we're managing to find other ways. Yeah, Pluto got demoted to a dwarf planet, and personally, I think that was a great decision because this is how science works. We change our ideas based on the new data available. Science is the continual progress. We update what we know. We used to think Pluto was a planet, then we got more data that showed us that Pluto was smaller than what we expected. Pluto got demoted as a planet. I think this was a very reasonable choice. It's proof of science evolving and changing its ideas to fit the data. So it's a good thing. Yes, we all miss Pluto. We had our mnemonics, we had our ways of memorizing the 9 planets, and then it's 8. But yeah, we demoted the planet named after the god of death. It's not like we brought on the end of the world or anything. Do we know the flavor of the high energy neutrinos detected by IceCube? I think it was mentioned somewhere. I don't know off the top of my head, but I think IceCube is mostly sensitive to muon neutrinos, but I might be wrong about that. So I'm not completely sure, but I might be in the release paper, which to be honest I haven't read yet because I am actually on holiday, so I haven't read any of the science release papers yet. Just like reading all the press releases, I'm getting hyped, but yeah, haven't actually gone in depth into the papers yet. Pluto never hurt anybody, no, but it's just not big enough to be a planet, and that's how science works. We don't think they were strawberry neutrinos, which is probably good because then you'd have strawberry ice cream. But yeah, I'm pretty sure they were either muon or electron neutrinos, but it's probably in the ice cube papers. But it doesn't. Yeah, it's very cool to figure that out as well. Okay, but then there was the other big announcement on Thursday, the big one. Not that the ice cube one wasn't big, but the big, massive, major announcements. Electron neutrinos are of stellar origin for the most part. Well, it really depends. I think it's a lot easier to produce electron neutrinos. The thing is, if you put the longer the distance that an neutrino travels, the more likely it is to change flavor. So the changing of flavor depends on the distance. So things that come from close by in the solar system have had less time to change flavor. So then you're more likely to measure the initial flavor of the neutrinos. Whereas if they're coming from far away, they can change flavor multiple times before reaching us. So that's the idea that if you measure an electron neutrino, it might be more likely to come from the sun or from close by because it's had less distance over which it can change its flavor. But the further away they are, the more chance that they're going to change flavor on their path towards us. David says, "I hope you're having a nice holiday." I am indeed, thank you. I've been off of work for 3 or 4 days, and I've caught up on a lot of like non-work projects and tasks and stuff that I wanted to do. And in 2 days, I actually head off somewhere on holiday. So first part of chilling at home holiday is almost over, and soon I'm actually traveling for the rest of my holiday. But there will still be a stream next week. Can we create neutrinos on Earth? And if so, can we direct them outwards for experiments? Yes, we can, and yes, we have. There are experiments on Earth. You get neutrinos. You get neutrinos, for an example, as a byproduct if you're doing any fusion type experiments. You can get neutrinos as a byproduct. And we have done experiments with them as well. And it's one of the ways that we go about measuring different properties of neutrinos. So we do know how to create neutrinos. You just need to reproduce the conditions in the center of the sun. Easy, right? Yeah, it's quite difficult to to reach the conditions we need to produce like a continuous stream of neutrinos, but we can produce them in some cases. You all might remember the famous paper a few years ago of, do neutrinos travel faster than the speed of light? That was because one accelerator was letting off neutrinos as a byproduct, and another experiment measured them, and they appeared to be moving a bit too fast. Turned out it was a faulty cable. But that was an example that we can produce neutrinos as byproducts on other experiments and then use them for data as well. First they came for Pluto and I did not speak out. Yeah. And then they came for everyone. Can anything stop a neutrino? Well, a black hole is going to absorb a neutrino. And a neutrino crashing into something and interacting with something else will stop a neutrino. A block of lead a light year in depth can stop neutrinos. I did not know that. That makes a bit of sense, yes. I don't think you can build a block of lead that is a light year big. I don't think we have enough lead for that, but hypothetically, one could do that. So yes, you can stop neutrinos if you have enough resources and time. I would not recommend building a block of lead a light year deep. No idea how you would even go about doing that. But yes, neutrinos are very difficult to stop. Okay, next major announcement. Gravitational waves. Now, I love gravitational waves, you might have noticed. Gravitational waves are ripples in the fabric of space-time. So in the same way that if you're going through water, you can create ripples, anything moving through space-time in a non-symmetrical way is going to produce gravitational waves. So that would be a lot of pencils. Indeed, you need a lot of pencils to get 1 light year of light. So if I'm spinning on my chair perfectly symmetrically, I don't produce gravitational waves. If I start moving around chaotically, I do produce gravitational waves. Anything that has acceleration and a lack of symmetry moving through space-time is going to produce gravitational waves. Things like 2 black holes spiraling around each other and then slashing together, huge burst of gravitational waves. Supermassive black holes, like the black hole is at the center of every galaxy when galaxies come together and crash and their supermassive black holes collide. Huge amount of gravitational waves. And things like small objects falling into black holes, gravitational waves. But also the universe itself can produce gravitational waves. We're pretty sure that in its infancy, the universe went through a phase of inflation. Inflation is exponential growth, as we're accustomed to today in a different context. We're pretty sure that the universe went through a phase of exponential expansion when it was very, 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 very small. And if it were 13.82 billion years ago, this inflation might have been so dramatic that it could have left a background of gravitational waves everywhere in the universe. And then there's other things like there might be something like a phase transition in the early universe. So in the same way, water can go from being solid to liquid to gas and back again. This is changing its phase. The universe could have done something similar, potentially. And depending how this phase transition happens, you could get bubbles of the new phase. These bubbles would expand, these would collide, and the collision of bubbles and the sound waves caused by these bubbles would produce gravitational waves. And that's what I'm working on. So there's a lot of different things that can cause gravitational waves. We have already measured gravitational waves coming from black holes smashing together, gravitational waves coming from black hole neutron stars smashing together, and once we measured gravitational waves coming from two neutron stars together. This is what we do with LIGO, Virgo, Kagra. These are Earth-based detectors, Earth-based satellites, Earth-based telescope, not satellites, Earth-based telescopes, L-shaped, kind of like this. You send the laser beam down each arm, it bounces back and forth off some mirrors, it comes back together. Based on how the light comes back and combines, you can tell if anything messed up the distance. If something messed up the distance, it's a gravitational wave. Because what a gravitational wave does is it distorts space and time. So first it will make you go in one direction and then in another. If a gravitational wave passes through you, you would first get thinner and taller and then shorter and fatter. But we're talking about a difference of a billionth the width of a human hair. So it's a ridiculously small difference. Would a phase transition now destroy the universe? Probably. If a phase transition were to happen today, it probably would destroy the universe. We don't think it's going to happen anytime soon, unless the Higgs is in a metastable state and we get a vacuum decay expanding ball of death in the universe. But it's quite unlikely. On the plus side, if we ever do enter a vacuum state, a vacuum decay, where the universe just decays to another vacuum state and creates this expanding bubble of destruction that not only destroys everything, it erases all existence of everything, we would never see it coming. It could have happened somewhere in the universe. It could be heading towards us at the speed of light already. We would never see it coming. So we don't need to worry about phase transitions. They're probably not going to happen. And if they do, they'll just wipe out the whole universe and we won't see them coming. Fun. I love talking about the expanding vacuum bubble wall of death in the universe. Unlikely. Probably. Okay, so we've already measured some gravitational waves, these tiny distortions in space and time, and we've measured the ones coming from black holes smashing together. But those are just part of the spectrum of gravitational waves. There's this image that you've seen multiple times in my stream by now, where we have different gravitational waves. On the left, you have the lower frequency. On the right, you have the higher frequency ones. And you can see on the right, you get things like rotating neutron stars, supernova, black holes smashing together, neutron stars smashing together. These are the ones we've been able to measure with terrestrial interferometers like LIGO, Virgo. Next, moving to the left, there are things that we hope to measure with LISA, the future space-based mission that is hoping to measure gravitational waves. It's hoping to measure things like supermassive black holes smashing together, white dwarfs in our solar system smashing together, and potentially these quantum fluctuations or these phase transition results. Then if you go to the far left of the image, you can use the cosmic microwave background radiation, my favorite thing in the universe, to measure the way light vibrates. You can use that to look for hints of early universe gravitational waves. And then there's the part that I barely talk about that is the focus of the rest of this, which is pulsar timing array. And you see pulsar timing array sits here right in the range where it can detect supermassive black holes smashing together and quantum fluctuations in the early universe. Okay, so let's break this down. Pulsar timing array. What are pulsars? What is pulsar timing array? What is this? Pulsars are dead stars, neutron stars. So when a star reaches the end of its lifetime, it can collapse, it can explode as a supernova, and then the core collapses. This core, depending on how big and massive the star was, this core can either be a black hole or a white dwarf or a neutron star. So a neutron star is a star that's really, really dense, dense enough that it can fuse electrons and protons together to make neutrons, but not quite dense enough to form a black hole. So it's kind of like a failed black hole. These neutron stars, dead stars, like the remnants of a failed black hole dead supernova star, can start spinning. Depending on how the collapse happens, they can spin. And these spinning neutron stars can often produce magnetic fields that spin around them. If this is the case, the stars end up with two jets. So you have the star with two jets. That's easier. These jets are jets of high energy particles that get accelerated in the neutron star and spat out along one of these jets. So you have your neutron star spinning with its jets, rapidly rotating neutron star. We call this a pulsar. And this is basically a cosmic lighthouse, because as this is spinning around, now you see it, now you don't, now you see it, now you don't, right? It's like a lighthouse. It's just spinning around, emitting this beacon of light. Some of these neutron star pulsars can spin so quickly that they spin thousands of times a second. These are what we call millisecond pulsars. So they spin thousands of times a second. I heard somebody say this is faster than your kitchen blender. I have no idea how to relate that to anything, but apparently these pulsars can spin faster than your kitchen blender. I feel like every blender is different and there are different settings, so that feels like a very weird analogy to me, but apparently that's some measurements. So, trying to do the rough math in my head, you won't even be able to get a ball of lead as big as the sun before it collapses into a black hole. Probably not, no. One could calculate that. We can calculate at some point how much lead you can put together, what volume before it collapses into a black hole. I leave that as an exercise to the reader or to the viewers. This is usually what you do in a lecture when you don't want to explain something. It's left as an exercise. Okay, so pulsars, rapidly rotating neutron stars, the lighthouses of the universe. These rotate incredibly precisely. They're like they're clock precision. They're like Swiss clock precision, which means you can use them as a timekeeping device. You can measure pulsars, and measuring pulsars lets you get a very, very good measurement of how time is passing. Because these pulsars should always spin consistently. They're not going to suddenly slow down or speed up. They just spin. Just do what scientists do, make up a random big number. Yeah, that's kind of our thing. Everyone has a number they default on. Make up big numbers. But pulsars, rapidly rotating neutron stars, it is strong enough to rip apart magnets. To rip apart atoms. These are the biggest magnets in the universe, and they're these lighthouses. So why is this important? Well, if the Swiss will be jealous of pulsars timekeeping. Pulsars, and we shouldn't do stereotypes like that. Apologies for that. But yes, pulsars are incredibly precise. So why does this matter? Well, if you remember, gravitational waves are ripples of space and time, which means if a gravitational wave goes through you, not only does it do that, but it also distorts time very, 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 very marginally. But if you have the perfect timekeeping device and you have multiple of these, then you can start putting them together to see if anything is affecting these clocks, anything such as gravitational waves. And this is what pulsar timing array is. Pulsar timing array, you take multiple pulsars, you string them together, and you turn them into a massive detector of gravitational waves. So we have measured 68 millisecond pulsars that we can use within our galaxy. 68 millisecond pulsars. This is quite a lot of pulsars. These are spread out across the galaxy, which means you can use them to build a galaxy-sized detector of gravitational waves. Using these dead stars, rotating really quickly, spitting out light caught in the magnetic fields of dead stars, and we use this to look for tiny, tiny, tiny ripples in space-time. Amazing, absolutely amazing. This whole concept is amazing. This is what pulsar timing array is, this idea that we can use these pulsars, the precise timing of these pulsars in pairs, to make sure we have the signal. You take different ones out, you do a lot of checking, and you use that to look for gravitational waves. It's incredible. And it's incredibly difficult to do. You even need to know like the overall average position of the mass in the solar system. There's something called the center of mass of an object, which is like the point where you can average all of the masses. And you need to know that for the solar system up to a precision of like 100 meters, because otherwise your pulsar timing array measurements are messed up. I'm guessing a true spacefaring civilization would use pulsars to sync up their clocks after traveling at high speeds. Yeah, potentially. Would it be possible to have a planetary system around a pulsar like that? So, apart from the no, not one that could have any form of life. So usually a supernova is going to destroy any planets that are in orbit around it. But if any survived, you would have a ridiculous amount of radiation, huge magnetic fields, solar winds or stellar winds, ripping apart any type of atmosphere. It would not be a livable place. You do not want to be in orbit around a pulsar. It's not a recommended holiday destination. Okay, so pulsars, rapidly rotating neutron stars. How do we actually measure these? We can use radio telescopes. Radio telescopes are these ones that have the huge dish. You might have seen them in the James Bond films and so on. These like huge dish radio telescopes. They're looking for electromagnetic radiation in the radio range of the electromagnetic frequency. And pulsars emit radio waves. So you can use these massive radio telescopes on Earth to measure the pulsars. And by measuring the pulsars, you can look for gravitational waves. Really, really cool. And this sounds like something out of a sci-fi book, and it should be. But this is something we can do. We've been doing it for 15 years now. So there are several pulsar timing array experiments ongoing. There is NanoGrav that uses radio telescopes in America. There is a European pulsar timing array. There is the Indian pulsar timing array. There is, I'm going to forget one. There is the Australian pulsar timing array, and soon there is going to be the Chinese one that is also joining, and you put them all together on something. You have a pulsar timing array collaboration with a bunch of radio telescopes performing this pulsar timing array analysis. They've been doing it for 15 years. NanoGrav, the US-based ones, put out results a few years ago. Yeah, there's going to be the Chinese one as well. So there was a NanoGrav 12.5-year signal or results, and then they all decided to coordinate. All of these pulsar timing array missions came together and said, let's do the 15-year data release together. The 15-year data release, the main results, this is the announcement on Thursday, a few days ago. So, of course, we have to answer the question, did they find something? What did they find? They found something. Then, obviously, else I won't be hyping this up. The pulsar timing array experiments have been able to measure the background hum of supermassive black holes smashing together. So we know that every galaxy has a supermassive black hole at the center. When these supermassive black holes collide, they produce gravitational waves. But there are so many of these events happening in the universe today and throughout the history of the universe that you're not going to find one event in the night sky. You're going to find the overall ripples. It's like if hundreds of boats go past, you're not going to say, okay, there's a boat, there's a boat. You're just going to see the ripples. The universe is vibrating with ripples from the merging of supermassive black holes. It's like the whole universe is vibrating with this back frequency, background frequency of gravitational waves of supermassive black holes smashing together. And now we've been able to measure this with the pulsar timing array experiments. This is incredibly cool. We're pretty sure that galaxies smash together. We're pretty sure that supermassive black holes exist and smash together. And now we have heard this background hum coming from supermassive black holes smashing together. And I'm going to throw a bit of caution here into the analysis, the same way the experiment people were, because they haven't passed a phi sigma threshold. Usually we want phi sigma. Sigma just gives you the statistical significance of your results. And usually we wait for phi sigma before claiming a discovery. Currently, the NanoGrav and the other pulsar timing array experiments are at about 4 sigma. So they're being very cautious, and they're phrasing it as first evidence of the background of gravitational waves and not a detection. But we have the first evidence of supermassive black holes smashing together and letting off this background hum. It's really, really, really cool. It's the start. It's become a cliche, but it's the start of a whole new way of studying galaxies and black holes and supermassive black holes. We don't know why there's a supermassive black hole at the center of every galaxy, and maybe this will take us one step closer to understanding it. And it's really, really cool. But there's a small chance that it might not be supermassive black holes. Supermassive black holes are very, very cool, but they're not the only possible explanation. If we go back to this chart here, pulsar timing arrays could measure two things: supermassive black holes smashing together, or quantum fluctuations from the early universe. So, amongst all of the papers that were released for the official announcement on Thursday, there was one of looking for new physics with pulsar timing array. And they found that you can also fit the signal with, for an example, a specific phase transition in the early universe, not a likely one, but you can make it work. Or even a network of cosmic strings, which are defects in space-time, like if you imagine cracks in space-time, that could also potentially fit the data. And even primordial black holes could fit the data. But supermassive black holes seem to be the best explanation so far. But the others are not ruled out. It wasn't enough to say, nah, it has to be supermassive black holes. 4 sigma is really, really good. And now we need to get more data to push it to 5 sigma. So supermassive black holes are probably the most likely explanation. But if that's the case, then there's another question. Because the signal is a bit too strong for supermassive black holes, which means either it's not supermassive black holes, or it's supermassive black holes and there's more of them than we thought, or it's supermassive black holes and they're more massive than we thought. All of these are really cool possibilities. So we have used dead stars with strong magnetic fields that trap light. We have used the timing between these spinning cosmic dead stars to look for gravitational waves coming from supermassive black holes smashing together, and we found something. We found this background signal. It's amazing. You know, some people were saying it's overhyped. It is not overhyped. It was, they could have hyped it up more, as far as I'm concerned. It was an amazing result. And I get it, 4 sigma, they don't want to claim a detection. It's a reasonable thing to do, but 4 sigma is already pretty cool. It's really amazing. And I saw someone just ask the question, do we still need LISA? Yes, we do, because they're looking for different things. If I bring this up again, if you look at the frequency of gravitational waves, pulsar timing array are looking for things that we need radio telescopes in order to measure. You know, the wavelength is massive. We've built a galaxy-sized detector with these pulsars in order to measure them. LISA is looking for different things. It's a different frequency band. So they're very complementary. They can work together. They're looking at different things. It's like if you have an X-ray experiment and a gamma ray experiment, they do different things. They can measure different things. But they are highly, highly compatible. Apart from the fact that this is like a really cool result, there's one more reason why I'm really excited about this. Still need to remember to drink though. Probably not an alien megastructure. Yeah, so Scott is saying here, you assume that everything clumps around a supermassive black hole. Might be, or maybe because you have so much mass at the center of a galaxy, then you can trigger the formation of a supermassive black hole. It's not completely clear. It's a chicken and egg story. We don't know which came first. Although I'm not going to enter the chicken egg linguistically argument. But supermassive black holes, galaxies, a bit unclear still. But one of the reasons I think this is so cool is the signal that I am interested in with LISA is this background signal caused by a phase transition in the early universe. This is what I'm hoping LISA will measure someday. We did see the CMB, actually. I accidentally put up the wrong slide at some point to show you all the CMB within 3 minutes of the stream, and nobody picked up on it. You did actually get flashed to CMB 3 minutes into the stream. And technically, there is a CMB on this image as well, bottom left-hand corner. So don't worry, you never miss that. So the thing that I'm interested in with LISA is the signal that lies behind everything else at the background. You know, there's a lot of other stuff in the way. And then there's a question of, if this background exists, would we even be able to measure it? Would we actually be able to pick up this distant humming of something vibrating in the background of the universe? Well, nanograv did. Of course, there's a lot of different things. There's a lot more things in the way when LISA goes up there, because LISA has to deal with galactic white dwarfs and a bunch of other things. But it's the idea that if a signal is there, we're not going to stop until we find it. Nanograv and the also other pulsar timing array people have found the first evidence of this background of gravitational waves, probably coming from supermassive black holes. Hopefully 20 years from now, 25 years from now, whenever LISA finally launches and we get all the data, someday maybe we'll be doing the announcement of we found the background radiation from something else in LISA. That will be amazing. It's an incredible result by itself. It opens a new way of studying galaxy formation and supermassive black holes. It's really, really, really cool. And it's just another idea that we know what we're doing with gravitational waves. We know how to measure them. LIGO, Virgo, Cagra are leading the way on the ground. Pulsar timing arrays showing us that we can measure this background as well. And in about 15 years, LISA is going to launch, and who knows what it's going to find. And I cannot wait. It's been a fun week in cosmology. We've had a lot of cool things. We've had the launch of Euclid. This is amazing. Euclid is going to help us map dark matter and dark energy. We've had IceCube looking at the center of the Milky Way with neutrinos. And we've had nanograv on the other pulsar timing array saying, hey, look, the universe is a lot more wibbly and wobbly than you expected. It's been an incredible week to be a cosmologist. We don't normally get this many good results this close together. And it's amazing when it happens. And every one of these individually could have been a whole stream. But they will happen within 3 days of each other. And they happened when I was on holiday, which means I spent the last 3 days just hyped up about all these results. Like, I don't have to do my own work. I can just be hyped up about everyone else's results. It's really, really cool. I did mention that they needed to figure out the position of the center of mass of the solar system in order for pulsar timing array to work. It's amazing. We will need a femtoroatal detector in the future. Yes. It's really, really cool. It's been a fun week in cosmology. Some weeks being a scientist is deeply frustrating. On some weeks, it's extremely rewarding and exciting. And learning about these things, hearing about these things, hearing them in the press releases. I did not have rumors or inside information about this before the releases. Hearing about this with everyone, sharing in the excitement, it's been amazing. I know some people were complaining like scientists shouldn't be hyping up their work. Why not? This is literally one of the best parts of the job. We have cool results. We get to share them with people. If anyone ever tells you scientists are being too enthusiastic, don't listen to them. Scientists are never being enthusiastic enough about work. We need more enthusiasm in science. It has been a good week to be a cosmologist. It's been very fun. And I hope I've been able to convince you all that all 3 of these results are awesome. Euclid is in space. We have gravitational wave backgrounds. We have neutrinos from the Milky Way. We know what we're doing. Scientists, we're currently looking at the universe saying, don't worry, we got this. We know what we're doing. It's been fun. It's been a great week. So this has been a very fun stream. I've just info dumped for an hour, as usual on these streams. I hope I've convinced you that cosmology is amazing and that there's a lot to look forward to in the future of cosmology. As always, it's been great fun to have you all here with the questions and the comments and the interaction. It's always great to see such a lively audience. It's always great to have you here. I am going to be on holiday for the next week, but I will still be doing a stream next week. I travel back in on Sunday morning, so hopefully I can do a stream on Sunday evening. I shouldn't be too tired. It should be fine. We don't need sleep to do a live stream. It's going to be fun. Cup of Cosmology should be back online next Sunday, same time as today. That's 7 p.m. if you're in Europe, 1 p.m. if you're on the East Coast of the US, 10 a.m. if you're on the West Coast of the US. As always, there is a time zone converter on cupofcosmology.com where you can put the next stream in your own time zone. Given that Twitter is slightly dodgy these days, you shouldn't rely on Twitter for Cup of Cosmology announcements. So make sure you subscribe to the YouTube channel to get all future notifications. Streams are usually advertised at least 6 or 7 hours in advance. And if you subscribe, you get the notification 30 minutes in advance as I'm about to go live. If you want to follow me for more personal ramblings, I'm on Mastodon at dchooper91 at tech.lgbt. You're all welcome to follow me there as well. I will not be posting on the bird site much going forward, other than for Cup of Cosmology news, if and when it's working. Twitter, not Cup of Cosmology. Cup of Cosmology is going to outlive Twitter at this rate. Never thought that would happen. Okay, I hope to see you all again next Sunday, same time as always. And I hope in the meantime, you all stay safe and take care of each other.